Hello and welcome back to CS210. This is for Module 11, our last module for the whole CS210. This is the first video, Introduction to Online Computation. So before we discuss about online computation, let's go back to the core of algorithmic problem solving, which is the definition of computation. Whenever we compute, we need to know the problem, which is just a pair of input and output specification. And then we have an algorithm solving that problem, or we have an algorithm producing that output. Sometimes that problem is easy, sometimes the problem is hard. That's why sometimes we use approximation algorithms for those problems na hard. Yung lecture for this afternoon, it's called online computation. So medyo naiba siya compared dun sa mga na-introduce na nating problems so far. So far, we've been dealing with problems called offline problems because before the start of the computation or before mag-run yung algorithm natin, we know the entire input in advance. And given the entire input, after mag-run ng algorithm natin, the entire output is produced. So far, like yung mga problems natin like search, sorting, ano pa ba, traveling salesman problem, and so on, are called offline problems. And it's running na ang model is offline computation because of the restriction that the entire input is given and meron tayong entire output after mag-run ng algorithm. In contrary, yung lecture natin for this afternoon, it's called online computation. And the main difference is that hindi na entire input yung given, but only a partial input is given. However, a portion then of the output is required. So we have a partial output na kailangang ilabas. So problems that have this restriction na partial input and partial output yung specification are called online problems, and algorithms solving those problems are called online algorithms. So here are some examples of those problems. Ito yung mga stock market problem, uh, K-server problem, paging problem, and of course there are online variants of well-known offline problems. For graph problems in general, we can imagine na meron tayong graph na nabubuo piece by piece, one vertex at a time. If the input is an array, then we can imagine na piece by piece din siyang pumapasok, one element at a time. And these problems are driven by real-world problems that are dynamic in nature. Not just yung fact na not available yung input, but because the output is also required. So formally, the online computation is modeled this way. So we have a vector I and a vector O to represent the input and the output that is revealed piecewise. So yung manner of having a piecewise input and output is modeled by parang discretizing the input. So meron tayong I sub 1 and the corresponding output na O sub 1, I sub 2, O sub 2, and so on. So at each time point, portion of the input is revealed. And the algorithm must produce also a portion of the output. So your algorithm runs iteratively from 1 to n hanggang sa matapos yung computation. And note that hindi po pwedeng maging infinite yung input sequence natin. Although in real world, pwede naman talaga na parang running lang siya. But madidisobey natin yung definition ng algorithm that the algorithm must halt. Right? So here, the input is finite. So we know in advance the total size of the input, which is n. And then we also have a condition that every time we decide or every time there is a partial output, irrevocable yung nire-release natin na part of the output. So we have irrevocable decision at every time point. Meaning, once it is produced, yung output is produced, you can no longer change yung na-produce mo na output. Okay? Even if you don't know the next part of the input sequence. So to illustrate how computation is done in an online manner, we have the following slides. So at time t equal to 2, we now know I sub 1 and I sub 2, and we are required to output O sub 2. Next is I sub 3 is revealed, and we are required to output O sub 3. So, to illustrate the irrevocable decision condition, hindi mo na pwedeng mabago si O sub 2 or si O sub 1 because ang kaya mo na lang ma-modify is O sub 3. Okay? So, at this point then, you may know na baka nagkamali ka ng pinili or naging part ng solution because you have a longer part of the input that is revealed. Pero, you can modify that na. Okay? Okay, so as mentioned a while ago, the computation is also finite. So the computation will end. So once the whole input is revealed, like revealed na si I sub n natin, at pagka-produce ng O sub n, dun na mag-end yung computation natin. Okay? So here's a concrete example. It's called the stock market problem. So the input here is the daily price of a stock from the stock market. So for example, it could be a particular share na nagbabago ng price per day. Okay, so per day you can get information about its actual price. Ayan. So to simplify further, daily na lang no yung price natin, although you can further discretize it to every hour, every second, and so on. And then your output is your decision as a trader whether you will sell your particular asset. Suppose may one asset ka lang to simplify the problem. You need to know whether you will sell your asset or to wait para maghantay ng mas mataas man na price. Your goal as a trader is for you to be able to sell your piece of asset, one piece of asset, with the highest price. Okay? So, in an offline manner, para mas madali siyang intindihin, your input is some P sub 1 to P sub n. And those are prices. You can imagine it as the parang sequence of prices lang, and your output is max of all those prices. Kasi, of course, you wanted to maximize yung pagbebenta mo ng one asset. So it's a get max ano lang 'to, get max problem. But mas mahirap siya because piece by piece lang yung nakikita natin, and piece by piece you also need to decide whether you will sell or we will wait. Okay? So here is an example. Suppose we have 6 trading days. Of course, you need to sell within this 6 trading days. So hindi pwedeng wait lang ang lahat ng sagot. Okay, so at necessary na 'pag naka-sell ka na, wala ka ng iba pang mase-sell pa to simplify the problem. So, to illustrate yung get max na problem in the offline manner, in the online manner, this is how it goes. So, for example, sa day 1, 10 yung price. You can decide whether you wait or you sell. Suppose you wait. For the next day, you have 20. What your answer niya is to wait then. And then for the third day, mag-wait pa tayo. 40 o tumataas. So, nag-wait pa tayo kasi mali mo, tumaas pa sa next day. However, for the fifth day, you receive the 5. Pero we're not sure, baka tumaas pa the next day. Okay. However, on the last day, since hindi natin alam yung price for the last day, naging 2 yung price, you're required to sell on the last day, which is 2. Okay, so the algorithm or the seller has a profit or has a score of 2, which is yung selling price on that day. However, the optimal solution should be 40. In the online or in the offline manner, if we know everything in advance, madali lang tong sagutin. You just get the max by doing linear search, or pwedeng better mga log n, di ba? Or n log n. You can get 40 easily. But since we don't know the price on the next day, since we have an incomplete input, it's very hard to be optimal. Okay? So, ano yung mga nagiging approaches for online algorithm solving this problem? We have the best so far algorithm. It's called the reservation price policy. The restriction of this algorithm is that we know the minimum and the maximum price. And based from the minimum and the maximum price, we can compute for some reservation price na somewhere in between the lowest price and the highest price. And ang algorithm will decide depending on the reservation price. So every time na nagkakaroon ng new price, we compare it to the reservation price. And if it's beyond or equal to that reservation price, magse-sell na siya. for as long as it is greater than or equal to some pre-computed reservation price. Okay? So if we will employ the reservation price policy for the sequence of numbers, we can get 30 as the profit, where the optimal answer should be 40. So it's not still an optimal online algorithm for this problem. But still, this is the best so far that we can get given deterministic algorithm. So, may mga other approaches din like randomized online algorithms. Sometimes it performs better actually compared to deterministic approaches. So, yeah, so that's the online problem and online problem for the stock market problem. So, given all the possible online algorithms, how can we assess whether that algorithm is good? For offline problems, of course, we have the running time complexity. We have the space complexity we wanted to be minimized. We have solution quality. Yung solution quality, it only applies to problems na hindi madaling i-solve, mahirap maging optimal. So, what we can do is to provide an approximation algorithm for those problems, and with respect to solution quality, we can judge whether we have a better algorithm or not for this particular problem. But for online algorithms, hindi na tayo masyadong magfo-focus sa running time and sa space complexity, because ang mahirap for online problems is getting the optimal solution because of the restriction nga na we have only partial input information. So, for online algorithms, we focus on the solution quality, and one way to judge whether an online algorithm is good or not is with respect to their competitive ratio. Okay, so yung competitive ratio is the corresponding solution quality metric na malapit din sa how approximation ratio is obtained. So we are basically comparing it to the optimal solution. How good is our online algorithm with respect to the optimal solution? So that's what we call competitive ratio. Hindi na tayo masyadong magfo-focus on the running time and space complexity. It is because it's very hard to be optimal even for problems na easy sa offline setting, nagiging hard kapag napunta na tayo sa online setting. So, most of the online algorithms are um, judged according to their corresponding competitive ratio. This is introduced by Slater and Tarhan in 1984. There are also several papers that you can read about competitive ratio. Most of them are using competitive ratio or competitive analysis in providing analysis for online algorithms. Pero hindi lang ito yung existing na measure solution quality for online algorithms. In fact, meron pang mga 11 other ratios. And if you're interested to look at those, we have this reference to consider yung mga different approaches. Mostly, yung competitive ratio lang yung ginagamit for most papers. But of course, may reason naman why they produce other metrics pa to measure. Now let's move on to the definition of the competitive ratio. This definition is very similar to the definition of approximation ratio because we're comparing the output of the optimal solution and the output of our algorithm given the same input. Here we have a constant C that is called competitive ratio. So basically you can just divide yung opt I and alg I natin to get some C. Depending on whether it's a maximization or a minimization problem, your C is either a value that is close to 1. Pwedeng bumaba sa 1, pwedeng mas mataas sa 1, depende kung minimization or maximization siya. Pero ideally, if your gain of alg I and gain of opt I is close sa isa't isa, then you have a C that is close to 1. Our ratio is not necessarily constant din. Sometimes it is described as a function. Yun nga lang, if it's a function, we can imagine this as an increasing function with respect to the size n. So, lumalayo ng lumalayo yung quality ng online algorithm mo as you have a longer input compared to a smaller input. If our algorithm employs a random number generator, then we can have a randomized online algorithm. Most approaches for online computation they don't just settle for deterministic approach. Gumagamit sila ng random numbers. And here, instead of calling it a competitive ratio, we have an expected competitive ratio because we also need to consider yung distribution of our random variable. Okay, so for online computation, we actually have several assumptions. The first assumption is that your input is adversarial, so the worst possible input could be an input. The second is decisions are irrevocable, so you can't change yung naging previous na sagot mo na out part ng output. And the online algorithm knows nothing about the input before they arrive. So, may mga approaches for online algorithms that try to relax a bit yung mga conditions na to. For example, merong mga online variants that try to relax the first condition. So, if yung first condition yung relax, then may certain predictability yung type of input that we are expecting. There are some relaxation on the second assumption. So, instead of irrevocable yung decision, sometimes we can modify a portion of the output na na-produce natin before. Most of the time, yung pinaka-recent na action pa pwedeng ma-change. And for the third relaxation, we can assume that the online algorithm knows something about the input. We can have an online algorithm na meron siyang lookup. So, even though you're just required to output, let's say, yung O sub 2 pa lang, you can get access to I sub 3. So, pwedeng single lookup, pwedeng multiple time lookup. So, that could also improve the competitive ratio of the algorithm. A more general approach for this third relaxation is by incorporating advice in computation. So, you can imagine advice as some external information that the online algorithm can have access to, like an advice tape. And this advice tape can contain some information. In general, you can input anything. You could put the entire input in advance. You could actually put the actual output in advance. Ang caveat lang dito is that this isn't very realistic in providing more competitive online algorithms, but the main intention is for classification of online problems with respect to the amount of missing information for them to be optimal or to reach certain competitiveness. So, this is very important in computational complexity, and yung area working on that is called advice complexity. And here's the model for online computation with advice. Instead of just the input provider or the adversary and the online algorithm having a sequence of input and output conversation, what we have here is another component, which is the oracle writing on a particular tape called the advice tape. Here the oracle can encode certain information, just like what I mentioned a while ago. It could be the whole input, it could be the actual output. And the goal is that the online algorithm and the oracle work together so that they can try to produce the best possible answer for the adversary. So, the oracle is a trusted entity by the online algorithm and knows the entire input in advance, and it also has no computational limitations. Based from this description, of course, obviously, yung mga online algorithms with advice are better than no advice at all. Ang dahil nga dito sa no computational limitation, the question is its practicality if it really exists. So, as mentioned, the main intention really for the advice complexity is for classification of the problems. So, the key for those who are working on online computation with advice is for you to be able to identify what sort of information can be encoded in a little most possible amount of space, encoded in either 0 or 1. So to give a brief description for that, there are certain problems such that either 0 or 1 lang ilalagay ni Oracle. They are the types of problems na kaya na maging optimal. One such example is the ski rental problem. So suppose you want to go to a vacation and you wanted to know whether you would buy the ski or rent na lang yung ski. But yung piecewise information dito is you don't know the weather pagpunta mo dun sa destination. So, the answer could be just rent the whole time or buy on day one. So, what we could put in the advice tape is the information as 0 or 1. Either buy a ski or rent all the time. Other problems require more information. For example, like the stock market problem. For us to have an online algorithm na laging optimal yung sagot, we will need the encoding of the entire output sequence.